Hello and welcome to our channel again. So where I am Suraj with a new video of mine where I will discuss about a very important thing in the quantum mechanics, which is the time independent wave equations or deriving the time independent Schrodinger wave equations. As in my previous videos, if you have seen, I have discussed about the infinite square well, where we deal with the time independent Schrodinger wave equation, not the time dependent, which is like this form. Okay, so it is very useful to use the time independent wave equations because it just remove our all the complexities and we can do very easy calculations. And when we do the time independent wave equations, we can easily derive the time dependent from the independent from the time independent. Okay, so this is very necessary to learn about the time independent wave equation. So in this video it is mainly dedicated to deriving the time independent wave equations. So now let's start our derivation on the time independent wave equation. So I have written here the time dependent Schrodinger wave equation. So this is a time dependent Schrodinger wave equations. So we will use to solve this particular equations by the help of the separations of values. So what we can do is that you know that psi of x of t, which is a wave function, is dependent upon both x and t. So we can just separate out as this particular psi of x, which is now dependent upon x, and phi of t, which is dependent upon the t. So now we're going to substitute these particular values of our psi of x of t in this particular equations, and what we get is that minus h cut square divided by the 2m. And what here we can write is del square psi. Okay, so del square psi of x also is there and phi of t is also there. Okay, so you can see that here is psi of x and phi of t. So we are going to put down the values of psi of x and phi of t in that equations, and you won't believe it will become very easy to derive the time independent in this manner. Okay, so now let's plug out these particular values. Okay, so what we can do is that we just put out the del square, okay, psi of x here and phi of t both here, and divided by with respect to, we are differentiating our this particular functions, which is the x, which is del x square, and plus we can write here v of psi of x, and phi of t, because we have written that potential is dependent upon time and position also. Okay, and which is equals to the iota h cut, and here you can say that of x and phi of t both. Phi of t, it means it is derivative of phi, and which is divided by the del of t. So this is our the most general equations. So what we can now do is that we are going to just dividing our, okay, so this is our equations become. And now what we can do is that, okay, first of all we have to do some changes, like we have to do is that if you look carefully here, we are differentiating the psi of x and phi of t with respect to the x. So with respect to the x, phi of t treats as a constant. It means we can take this out from our partial derivative, and now what we can write is that minus h cut square divided by the 2m, and phi of t is taken out as a constant because we are partial derivating these equations with respect to the x. And now we can write is as del upon del. Okay, so now what we can do is that we can write is like the del square only psi of x and divided by the del x square, and just leaving out our potential energy the same, which is v psi of x and psi of t. Okay, now doing right hand side, the same thing that we have done on right hand side, we are partial derivating with respect to the t. It means psi of x is now treated as a constant, and we can just put this out from our equations. And so our equations look very simple now. Okay, so now our equations look like a very simple equations. So this is our final form of the equations that we obtain. Now what we are going to do, so let's say this is our equation number one. So let's say this is our the equation number one. So what we are now going to do is that here is that we are going to dividing our this particular expression, this particular thing, which is now what we are going to do is that our this particular expression, okay, so our this particular expression is getting divided So we are going to dividing this particular by psi of x and phi of t on both sides. On both sides, we are going to divide our equations with by dividing equations by psi of x and phi of t. So now we are going to write this in a more general form by just putting this out. So what we can do is that we can write it as the minus h cut squared divided by the 2m. So if we divide here, the phi of t and phi of t will cut out, and what are we left with is 1 divided by the psi of x, and here del square psi of x and divided by the del x. Okay, so I'm not writing here x because you can understand that this is dependent upon the x, and plus the potential will leave out because this and this will completely cut out, and it is equals to the iota h cut 1 over phi of t, which is now becomes, which is it, because the psi of x and psi of x will cut out and we are leaving with this, and this is equals to the del phi divided by the del t. So okay, now we are moving towards more general expression. So this is our expression. Now we are going to derive the time independent from this expression. So what we can say is that in general, the quantum mechanical particles are like doing the the oscillatory motion, the harmonic oscillatory motions. And in harmonic oscillatory motion, you can say that the energy is a constant, because when I will teach you about the SHM, okay, and any type of the other harmonic oscillations, you can see that the energy is constant. The energy is a constant in whole of this harmonic motion, just like in SHM you can see that. So harmonic motions and periodic motions, it means particle is moving again and again from its mean position to its extreme positions. So now let's just graphically that this is a particle, and this, suppose this is our the mean position, and this is our the extreme position. Let's say this is a, and another extreme position, let's say the minus a, and the particle is moving again and again on this particular trajectory, and you can say that the kinetic energy is converted into the potential energy, and the potential energy into the kinetic energy, and whatever this, and this has the constant energy. It means what we can now say is that iota h cut 1 over phi of t, okay, phi of t del phi divided by del t can be written as is equals to the energy of that particular particle, because this is the total energy, and we can equate this with like this. So yeah, we can equate this like this. So now what we can do is that we just shift out this particular from right hand side, and what we can get is that, and also the all constants to the right hand side, and we are only left with the d psi, because now we are going to dealing with only one function here. That why I replace the partial derivative with the normal derivative, and this is equals to the 1 upon iota is minus iota, remember, e upon the h cut, and here is equals to the phi, which is dependent upon the t. So now this becomes a differential equation. So now this becomes a differential equations, and you can easily solve any type of the differential equations. So in general, I am going to writing out the exact solution of this particular expression. So I am going to just writing out the general solution of this particular expression, and the general solution of this particular expression can be written as phi of t, okay, phi of t. General solution is this particular expression is known as phi of t is equals to e to the power minus I omega t. So this is what our equations become, and I'm writing here that you can also write in this form, where omega is equals to the e upon the h cut. Okay, so omega is equals to the e upon the h cut. So I'm just substituted the value of omega and e upon h cut, and we get our value. But no, this is very simple. Okay, so this is our general solution of this expression, phi of t. So this is our time dependent the time dependent function value, and this in the time dependent Schrodinger equations tells that how our quantum mechanical system is evaluating with respect to the time evolutions of the things. Okay, so this is our solutions. So now just equating our second equation, the second equations, which is the minus h cut square divided by the 2m, and here you can see that we are just dealing with the normal derivatives because it is now becomes the function of only one, so it is now 1 over psi of x, and here we can write it as only in the normal derivative sign d psi, sorry, yeah, d psi divided d sorry here, so we can write it as the d psi divided by the dx, so d square psi and dx square plus the potential, and we can also equate this with the total energy, as I have discussed that this is an harmonic oscillator, and generally the particle is doing like this, and and there is a constant energy. So now what we can do is that multiplying this is what our equations become. So what we can do is that multiplying this equation by the psi of x. So we are going to multiplying these equations by the sign of x, psi of x, which means this and this will cut out, and what we are left with is minus h cut square. So it is cut. Okay, so minus h cut square divided by 2m d square psi divided by the dx square, and plus here v psi, where psi is the function of x alone. Okay, so this is not the psi that is in the time dependent form, and this is equals to the e psi of x. So this is our or you can say that it is our time independent Schrodinger equation, and this is a very important equation which you have to remember, because whenever we deal with the quantum mechanical systems, potential systems, we generally use our this particular expression, which is now only convicted to only reduced to one constant, which is the one variable, not constant, one variable, one function, which is the x, not on the time t. So here I have tried to explain that how we can derive the time independent wave equations from a time dependent wave equation. So there may be some other methods, and I will also make a video on some other methods of proving this particular time independent Schrodinger wave equation. Okay, so thank you for watching my video on this small topic, time independent Schrodinger wave equations. And next video is also going to be very interesting, in which I will discuss about some potentials in quantum mechanics. I've discussed one potential, which is infinite square well, but we are going to also discuss about some other potentials. So this is today's video of mine on the Schrodinger wave equation. So thank you for watching my video, and if you have any doubt, you can tell me in the comments.